now is to find something to timestamp event such that if one timestamp is less than the other, then we can actually say that there is an happened before relationship between the two events. And the intuition, the first intuition, okay, these are the vector clock, and is something that is usually explained to you as a vector or numbers. But in order to understand really what happens, we have to look under the hood of these vectors, and we have to understand why and how these vectors are created. So in order to do it, we will create vector clock incrementally, starting with the idea that is behind the vector clock. So the first intuition that we have is that a timestamp has not to be a number, right? Has to be an object. Any object that we can compare is fine. It has not to be a number. We can compare other objects in real life. We can compare other mathematical structures that are not only numbers, and we can create meaningful way to compare them. So let's say that for a timestamp, when we timestamp an event, we include in the timestamp the entire history of the event and the event included. So for entire history, I mean that I include all the events that have happened before you and have causally influenced you. So the timestamp I will start by describing the timestamp, and then I will say how we can create it using distributed rule. So the timestamp for each event, let's say that we are just on a system of two processes, and the timestamp for the event is a list of history, and you have one history for each process of the system. Each history is a list of events and is the list of events that happened on a specific process. So in this case, for event E0, we have the timestamp of E0 that contains an history that is P0, that is the history of event that happens on P0, and this history of event will be a list that contains just an element, and this element E0, because no event on P0 happened before E0, so E0 is the first event. Remember that we include the event in the things that casually created it. And then this timestamp has also the history of P1 inside, and the history of P1 inside is empty because event E0 does not know anything about P1. When E0 is created, process 0 does not anything about P1, and so the history will be empty because you have no information. And then for event E2, we'd have to put the things that casually created E2 and are E0 and E2, the two events that were created on P0. And then for the same reason that we said before, the history of P1 inside the timestamp that we use for event E2 will be empty. Then we have on process P1 the symmetric thing for event E1. So we have that the event E1 will have a timestamp, and this timestamp contains the history of event on P0 that have casually influenced the E1 and is empty because no event on P0 has casually influenced E1. Then we have the history of the events on P1 that have casually influenced the E1, and E1 has been casually influenced by E1 itself on P1 because we said that we include the event on the history. And then we have the first interesting thing, that is the receive event E3. And notice that the receive event E3 is the receive event that is connected to the send event E2, because E2 was the send of message M, and E3 is the receive of message M. And so in this case, we have that event E3 depends on event E1 on P1, because E1 happens before E3, and it's easy to see that they are casually related. But also we have that the message is creating a causal relationship between event E0 and E2 and event E3. And so we have to put in the history of event E3 for the location that we use for P0. So history P0 on event E3 in process P1 becomes E0, E2, because E0, E2 are events that happen on process P0, okay? But casually influence E3. And so they go there. And for event E4, we have the same thing of event E1. So event E4 depends for the history of processes of P1, it depends on on P1, it depends on E1, E3, E4. This is the list of event on P1 when E4 happen, including E4. But we also have that E4 causally depend by E0 and E2, right? So we have to take the history of E0, E2 inside E4 for the history of P0. And now we have to see how we can build these things in a distributed way. And we have just to use two rules. The first rule is the update send rule. So when you create an event, I'm just saying that local events are send, but does not matter. The local event can also be something different of send. What you do is that if the event that you are creating is not a receive event, what you do is that you append the event to the history of yourself and you append it. So let's do it with an example. We have the timestamp of process E0 is just the history with E0, sorry, the history on P0 with E0 and the history of P1 that is empty. Then we create event E2, and what we do when we create event E2 is that we take the timestamp of process of event E0 and we add, since this event is happening locally on P0 and is a send event, what we do is that we append the event E2 on the list in the last location of the list P0 that was in the timestamp of event E0. So we take the history of P0 that was in the timestamp of event 0, we append to it E2, and then for all the other history we take the same, and then we timestamp the event send that we are creating with this thing. And then we send this message with this appropriate timestamp. And then we need a rule to update when we have received event. And the rule is this one. When you receive something that contains a timestamp, but you also have a timestamp of an event that was happening before you on the same process. If there was no event, we imagine that we have the empty event that is just a timestamp in which each list is empty. And so what we do, let's do the example with E3. What you do is that you take the timestamp that was before E3 and is the timestamp of E1. You attach event E3 in the history of P1. So you attach E3 after event E1, and then you have to distributedly build the history for process P0. But what you do is that you look at the history of all the other processes that are different from you, and you compare the history on the message that you receive with the history in the message that you have in your memory, so your all the timestamp, and you compare it and you take the newer version. So the newer version, the newer history is the one that that the message is carrying, and is the timestamp that we have associated with the send event E2. And this history for process P0 contains event E0 and E2. The history for process P0 on event E1 that happened on process P1 is just the empty list. So the newer version is E0, E2. And what you do is that you add the newer version in your timestamp, you substitute it. So we create the timestamp of E3 that will contain the history of P0 from E2 plus the history P1 of E1 in which we append the receive event E3. And so in this way we are distributedly creating these events. Sorry, these timestamps or event. And now what we have to show, is that between this timestamp we can create an ordering relationship. So we can decide when one of these timestamp is greater than the other. And this is something a bit confusing at first because these timestamps are not numbered, but follow me and you see that you can create some kind of partial ordering relationship between them. So, and I say that one event is greater than the other if for all history I can find that the smaller event, the timestamp of the smaller event the history. So the timestamp of the smaller event for all history, when we extract the history, it contains history that are a subset of the greatest timestamp of the greatest timestamp. And then there exists an history that is strict, that is a proper subset. So let's make it clear with an example. Let's take the timestamp of event E3 and the timestamp of event E2. And in this case, we have that the timestamp of event E3 is greater than the timestamp of event E2. Why? Because the first history the history of P0 is equal on both processes, so we can say that the history on the timestamp of event E2 is included, is a subset of the history that is contained in the timestamp of event 3. And this is obvious because E0, E2 is a subset, is included in E0, E2, right? And we can also say that the history of P1 on the event, on the timestamp of event E3 is strictly greater than the history of P1 in the on the history of P1 in the timestamp of event E2. Why? Because the history of P1 in the timestamp event E2 is just the empty list, while the history of P1 in the timestamp of event E3 is a list of 2 elements. And so the empty list is a strict subset of a list of 2 elements. And this is how we compare event. And now we say, I have to show you the intuition on why, if one event happens before the other, then the timestamp of the first event is less than the timestamp of the other. And the intuition is that when this happens, the timestamp of the event E prime that happens after E will contains the timestamp of event E. And you can try to do it and you will see it that is obvious. The example is, for example, event E2 and event E3. E2 brings its timestamp. And what you do is that you look at the new history and then you update something. And by doing this, you are creating always something that is strictly containing the timestamp of event 2 when you created the timestamp of event 3. But we have also to show the other way around, because there was the thing that we were trying to construct, right? Was that if one timestamp is less than the other, then one event happens before the other. And the intuition, let's say that the timestamp of E prime contains E. Then it must exist a causal path from E to E prime. This is the intuition. Why? Because if I timestamp of some event that we are constructing with this list contains E, then it means that you received something that contained E inside. And this could be, for example, the send event EU. And so it means that there must exist a path that connects you to E, because you have visibility of E. So you have received some information that contained E inside. And so this information can only be generated by event E itself. So it means that there is a path that connects the event that has a timestamp that contains E with event E. But this path is actually a path that is creating a causal relationship. And so this is why it works also in the other way. This is why if we say that an event is less than the other, sorry, a timestamp is less than the other, then also the corresponding event are causally related. And now we have to engineer this solution, because sending this kind of structure that are list of events is not good for several reasons. So one example, when we send a message, we have to send the entire messages that happened before it, and they can, grow and occupies a lot of space in a message. So we want to have something that is more performing, that occupies less space, but that has the same power. And the first observation is that you have to answer to this question is that it's not possible to have two events, E and E prime, such that their timestamp have for a certain history, two history that have the same number of elements, but they are different for the same process. So it's not possible that we have an event E, and it's not possible that we have an event E prime such that the timestamp of E contains an history of a process Px, and this Px contains three events, as example E0, E1, E2, and then the timestamp of E prime contains always the history of process X, but that contains event E0, E1, E3, so that they are different. And why is not possible? Because if you look at the rule, the only one that touches history Px on messages is always process Px. So you are the only one, if you saw the rule that we used, you are the only one that increase your history. And since you are the only one that you increase your history, it's not possible that at a certain moment you create two different messages in which you start from event E1 and you generate something that contains that for which we have event E2, and then you generate something else for which you also have event E3. It's not possible if you are correct, because when you append something, you are creating a new list that has a new size, and so you cannot start from a list of size 2 and you append two different things in the same position. Okay? So it means also that it's not possible that we have two strings, two histories that have different sizes, and such that the smallest one is not a prefix of the other. This is also not possible. So when we have history that have different sizes for the same process, of course I'm talking about the same process, then they have to be, one has to be the prefix of the other. The small one has to be the prefix of the other. So it's not possible that we have an history inside a timestamp of px that contains e0, e1, e2, and we have inside another timestamp a history of px that contains e0, e1, e3, e4. And this is for the same reason of before. So you have that the only possibility is that the longest history is e0, e1, e2, e4. So it's not possible that contain e3. But remember that we were saying that one history has to be included in the other. And this means that we can substitute this kind of notion with just one history is a proper prefix of the other for the strict inclusion, not a proper prefix for the not strict inclusion. And then it means that we can just say that one history is less than the other. And this is enough, because they have to, I mean, they are always increasing lists that have the same prefixes. So, for example, let's look at the event on process 0, and will be on the event E2 and the E3, and we will be convinced of it. So, event E2 contains an history of P0 that has two elements, E0, E2. Event E3, if contains an history of two elements for P0, has to contain E0, E2. So it means that if the list on the history of P0 in timestamp of event 2 is as just length 2, and the history of process P0 in timestamp of E3 as also length 2, it means that they contain exactly the same element. It also means that if the list on E3 is greater, this is the case, but if it was greater, then it means that the history of the smallest one was included in the history of the largest one. So we can look at it on process P1. We have E3, E4, and we have the history of P1 on E3 as contains just two elements. The history on process 1 of E4 contains three elements. And we can see that the smallest list is included in the largest one. So we can just use the length of the list to see this inclusion. So it means that we can compress this data structure and just we use lengths, and the things does not change, because if a length in a certain location that now corresponds to an history of a certain process is less than the length of the same location in another event, then it means that the corresponding list from which we were starting has to be included in the list of the largest location. So let's look just an example. The example is E1 and the E3. We have that the len of the history of P1 on E1 is just 1. The len of history of E3, the len of history of P1 in the timestamp of event 1 as size 1. The len of the history of P1 in timestamp of event 3 as size 2. And this means that, of course, the list of history P1 in the timestamp of event 1 has to be included in the history of P1 in timestamp of event 3 for all the argument that I said to you. So it means that if we substitute this structure with a structure that contains a location for each history, fixed location that has to be the same on every process, and a number, then if we see that in that location a number is greater than another, we know that the corresponding list is included in the other. So this is try to do a bit of example in this figure, and you will see that is as I said. And so these are the vector clock, and we just replace the things for the ordering that I say with another rules, and we say that if an event is greater than the other, then it means that all the location on one clock have to be less or greater than the other clock, less or equal than the other clock, plus there must be one that is strictly greater. So to be precise, let's do an example to clarify things. We have process E2, and process E2 has a vector clock that contains Q0. We have process E3 that has a vector clock that contains Q2, and we have the first component of E3 is 2, and 2 is greater or equal than the first component of E2, and we have that the second component of E3 is 2, and this is strictly greater than the first component of E2, that is 0. And so it means that the timestamp of E3, the vector clock, is greater than the timestamp that the vector clock of E2. But there are also non-comparable vector clock, and are the one of E0 and E1. So the first location of event E1 is 0. The first location of event E0 is 1. So we have that for that location, the timestamp of E0 wins. But for the second location, we have that the timestamp of the event E1 is greater than the timestamp of event E0. So in this case, the timestamp of 1 wins. What does it mean? It means that these timestamps are not comparable for our rule, and it means that these events are not causally related, and so they are concurrent. So the vector clock captures causality in a perfect way. In such a case, we say that if two vector clocks are not comparable, then the corresponding events are concurrent. And this is a definition of vector clock that you can have. If you don't want to go through the list, there is just this definition. And so you have an array of n integer, and each process you maintain n integer because there are n processes in the system, and you have a location for each process that is fixed as this one that correspond to the ID of the process. Remember that we imagine that we have ID that are mapped between 0 and n minus 1. And these vector clock are attached to messages as for scalar clock, and we have seen things for the list. And then when you initialize your things, you set all the location of your vector clock to 0. And when you generate a new event, you increase just your location of the vector clock by 1, and you use this rule. The first rule is the send of a message. So when you send a message, you create an event send message. So this means that you increase the location on yourself, so that you increase your location in the vector clock. So if you're process 0, you increase the location 0 of the vector 1, then you create a message, you timestamp the message with your vector clock, and you send it. And then we have the rule when you receive a message. So when you receive a message contains a vector clock, you scan all the location of the vector clock that receive, you scan all the location of the vector clock that you have in your memory, and you take the maximum between the location. And then what you do is that you generate a receive event. So what does it mean? That once you have done this merge of clock, by taking the maximum on each component, you increase your component by 1. So let's say that process 0 receives something from process 1 that contains a vector clock that is 0, 1. Then you merge this clock with your clock, and then you increase your location. So we will see an example shortly. Okay, and we say that two vector clock are equal if they are equal in all the location. We say that one is less than the other, less or equal the other, if all the location of one are less or equal to the location of the other. And then we have to say that if one is strictly less than the other, and this is what interests us, and we say that they are one is less or equal than the other, so all the location are less or equal, and there exists a location that is strictly less. So we will see it with an example to clarify. This is an example of two vector clock, or 4 vector clock. So the vector clock on the upward pair are vector clock of events that are causally related. So the first event, the one that happens before, are a vector clock that is 1, 2, 0. The event that happens after has a vector clock that is 1, 2, 2. And you can see that the first location of the second event is greater or equal of the one of the first event. The second location of the second event is greater or equal than the one of the first event, because 2 is greater or equal than 2. And then you can see that the last location of the second event is strictly greater than the last location of the first event. And so in this case, we say that E prime happens after E. Notice that when I say appends after, I mean just the opposite of appends before. And then for the pair that we have, the downward pair, we have that there is no causal relationship between the event that are concurrent, and this is reflected by the vector clock, because the first component is equal for the both event. In the second component, the first event wins on the other, because we have that 2 is greater than 0. And the third component, in the third component, we have that the other event wins. So in this case, the component of E prime is greater than the component of E, and so 2 is greater than 0, and this means that the vector clock are not comparable. And it means that these events are concurrent. And this is an example. So let's do the example together. We have process 1. Process 1 starts with a vector clock that contains 0, 0, 0. And in this case, I'm not using 0, but just a line to indicate 0, and it's the same things. I create an event, so I increase 0, 0, 0, and I create a vector that's 1, 1, 1, because I have to increase my component, and P1, so it's the first component of the vector by 1. Then I create another event, and I increase the component of the vector by 2, and I attach my vector clock that is 2, 0, 0 to my message. My vector clock that is 2, 2, 2, 0, 0 reaches process P2, and this means that P2 create a new vector clock that is the merge of the vector clock that it received and the vector clock that it had. Since this is the previous event on E2, on P2, we can imagine that P2 has a vector clock that is 0, 0, 0. So what you do, for the first component, you see the maximum between 2, that is the timestamp, that is the first location of the vector clock that you receive, and 0, that is the first location of your vector clock, and you take the maximum that is 2. Then for the second location, you take the second location on the vector clock that you receive, and the second location of your vector clock that is 0, and you take the maximum that is 0. And then you take the maximum, the third component that is also 0. But then you create also a local event that corresponds to the receive of a message, and it means that you increase your component by 1. So this is why the vector 2, 0, 0 becomes 2, 1, 0. And then on process P2, on process P3, we have an event that happens, and this event is concurrent because it creates a vector that is 0, 0, 1. And 0, 0, 1 is concurrent as a vector clock with 2, 1, 0, because we cannot compare them. They are not comparable. Then on process 3, you create a new event. So you take your vector 0, 0, 1, and you increase your component that is the last one, and you obtain the vector 0, 0, 2, and you attach this vector to an event. You send this event on process using a message to process P2. So you create a message, you attach this timestamp 0, 0, 2, and this timestamp 0, 0, 2, this vector is received by process P2, and P2 do the maximum component and then increases its component. So the maximum between 2 and 0 is 2, so the first component of the vector is 2. The maximum between 1 and 0 is 1, so the second component of the event will be 1. The maximum between 0 and 2 is 2, so the third component will be 2. Then you create a local event that is a receiving event, so you have the vector that is 2, 1, 2. You increase the component in the middle, and you have the vector that to which you timestamp the receive that will be 2, 2, 2. Then you create your send event, and you have to increase your component by 1, that is the middle one, and you create something that is 2, 3, 2. And you send this event, this event is a send message to process 1, you send this thing with the vector clock that has to be included, and then process 1 receive this message, and this message contains a vector that is 2, 3, 2. So what you do is that you do the maximum on the first component between the vector that you receive and the vector that you had in memory. And in the meanwhile, on process P2, we also generated another event. So the vector that was 2, 0, 0 become 3, 0, 0. And then you do the maximum between 3 and 2, because 2 is the first component of the event that receive. We are timestamping event E for 1. And so it means that the maximum is 3. Then we do the maximum of the component in the middle, and is 3 and 0, and the maximum in 3. Then the maximum between the last component, 0, 2, the component is 2. So we have 3, 3, 2, but we have to create the receive event. So we have to increase our component that is the first one by 1, and we get 4, 3, 2, and so on. So notice that these things is capturing causality, because we have that the vector 0, 0, 1, that is the event of E3, 1, is less than the vector 4, 3, 2, that is the event E for 1, and these events are causally related. We can find the path, and the path is event E3 1, first element of the path, event 3 2. 3 is the process number. I'm reading first the process number. Event E3 2, that is the second event on P3. Then we have event 2 2, that is the second event on P2. Then we have event 2 3, that is the third event on P2. Then we have event E1 4, that is the fourth event on P1. But we also have that two vectors that are not comparable capture the concurrent relationship. The concurrency is not a relationship, it's the lack of ordering between two events because they are concurrent. So we have that the last event on process P1 and the event as a clock that is 432. This one is concurrent with the last event on process P3 because the last event on process P3 has a vector that is 303. And if we try to do the comparison between vector 432 and 303, we will see that does not work because the first component on 432 is greater than 432. So the first component between the timestamp of the event of the last event on process P1 and the last event of process P3 wins the last event on process P1 because it's bigger. For the second component wins the last event on process P1, but for the third component with which winner, and the winner is the last event of process P3 because the last component of the timestamp of that event is 3, the last component of the timestamp of the event on process P1 is 2, and 3 is greater than 2. And so this means that these vectors are not comparable, and since they capture causality, also the corresponding events are concurrent. So this is an exercise that you can do, try to do it. This is another exercise that you can do to exercise on vector clock, and then you can try to identify the false statements using this example. And so we have seen logical clock and vector clock, and they are two powerful tools that we can use, and they have different use. So you don't have always to use vector clock. You can always use logical clock, even if a scalar clock or logical clock is the same, even if they are a bit less powerful, because there are applications when these things matter. And one of these applications is the Lamport mutual exclusion.